Swayam Prabha. Digital India. Educated India.
Welcome to this lecture on transition metal organometallic chemistry from principles to applications. We have been discussing about transition metal carbine complexes, and we have looked into the reactivity of these transition metal carbine complexes in the last lecture, and what we had seen that these transition metal carbine complexes add to nucleophiles and undergo some other kind of reactions, for example, reductive coupling and so on and so forth, and they do all these as a part of the reactivity study, and what one ends up is the formation of transition metal carbene complexes. So, these were part of the reactivity studies that we had seen. In our previous lecture. Now, at this I would like to note that the formation of carbene complexes from the reactivity of the studies is akin to the going in the reverse direction, where we have prepared the transition metal carbine complexes through various method from the corresponding transition metal carbene complexes. So, these were preparative studies of transition metal carbine complexes. So, we see that the cycle completes itself when we look at the property studies and reactivity studies of transition metal carbine complexes. By that I mean that these transition metal carbine complexes can be prepared from transition metal carbene complexes by a number of synthetic procedures that exist, and when the reactivity studies of these transition metal carbine complexes are carried out, they can also be converted back to the transition metal carbene complexes through much of the reactivity studies that we had discussed in our last lecture. Now, today in this lecture I am going to focus some more on these reactivity studies that can be done with transition metal carbine complexes. And one important reaction in this regard is transition intermolecular carbon transfer reaction. Now, let me mention this in context of the transition metal carbene chemistry that we had discussed. The transition metal carbene reagents are not too good for a source for transition metal carbene transfer reactions, and that the chances of obtaining free carbenes from transition metal carbene complexes were rare, and there were few examples which are known for transition metal carbene transfer reactions, where the carbonic moiety has been transferred onto some organic substrates, particularly olefins, leading to formation of cyclopropanes, and these were achieved both chirally as well as achiral in achiral fashion. Now, with respect to carbine getting transferred, there are not too many examples where these transition metal carbine complexes exist as carbine transfer agents, and here I discuss one rare example of intermolecular carbine transfer reactions, in which the carbonic moiety gets transferred in the course of the reaction, and this is for the complex X CO4 molybdenum Cr carbine moiety when treated with cobalt 1 - 2 - 3 - 4 - 5 - 6 - 7 - 8 - 9 - 10 - 11 - 12 - 13 - 14 - 15 - 16 - 17 - 18 - 19 - 20 - 21 - 22 - 23 - 24 - 25 - 26 - 27 - 28 - 29 - 30 - 31 - 32 - 33 - 34 - 35 - 36 - 37 - 38 - 39 - 40 - 41 - 42 - 43 - 44 - 45 - 46 - 47 - 48 - 49 - 50 - 51 - 52 - 53 - 54 - 55 - 56 - 57 - 58 - 59 - 60 - 61 - 62 - 63 - 64 - 65 - 66 - 67 - 68 - 69 - 70 - 71 - 72 - 73 - 74 - 75 - 76 - 77 - 78 - 79 - 80 - 81 - 82 - 83 - 84 - 85 - 86 - 87 - 88 - 89 - 90 - 91 - 92 - 93 - 94 - 95 - dicobalt octocarbonyl gives CO9 cobalt eta 3 Cr. This is tricobalt alkylidine cluster along with CO6 cobalt 2 eta 2 RCCr complex. This is alkyne pi complex. So, what can be seen over here, that in this molecule there is intermolecular carbene transfer reaction happening, leading to formation of a tricobalt alkylidine cluster, where the metal ligand multiple bonding character is lost. Where the carbene loses its metal ligand multiple bond character, and as similar to what we had seen in metathesis reactions, that formation of a pi complex with the metal is also observed. Now, this kind of metathesis type reaction was also noted for the corresponding carbene counterpart, where olefin was formed from this kind of reaction. So, we do see that there is a parallel reactivity of transition metal carbene and transition metal carbene kind of complexes for this kind of carbene transfer or carbene transfer reactions. This transition metal carbene complexes also undergo electrophilic attack by proton. And this can be explained by this reaction ln m C R. Now, the attack can happen at carbon or at metal. So, when it reacts with HX, that leads to elimination of X minus. So, giving the proton, and then proton attacks the pi cloud, resulting in formation of this cationic species, or the results can also happen at carbon, giving this L n minus 1 X M H R. So, depending on the metal and depending on the ligand, one can see attack by proton can happen both at metal and at carbon. So, here we see an interesting reactivity of proton towards carbonic center, where the proton can go and attack the metal, as well as it can attack at the carbon and undergo addition of HX to give a transition metal carbene complex. So, what we see that there is a differential reactivity as to which attack may take place, and that all depends on what kind of ligand is surrounding at the metal and what kind of metal is forming this carbine bond. Depending on the these one or the other modes of attack would be favored. Another interesting example is that of conversion of the carbine complexes to C minus as ultimate organometallic ligand. So, this is an interesting example where transition metal carbine complex is this is the carbine complex is converted to carbido. Carbine complex converted to a carbido complex. Now, this carbido is a very interesting ligand. This is ultimate organometallic ligand, because there is fully carbon and there is no other substituents on the carbon, and this is a C minus kind of species, and these to be obtained from transition metal carbine complexes, but this only occurs when there is a special criteria of R equal to being hydrogen. Okay. So, when the carbine complexes having R equals hydrogen is obtained, that can be converted to the ultimate organometallic ligand, where this carbonic moiety is converted to a carbido moiety, as seen over here. A nice example of this is discussed here, where AR R N R equals T butyl. AR is a bulky ligand 3,5 dimethyl C6H3 molybdenum N R air N R air reacts with carbon monoxide to give CO N R air N R air N R air. Now, this undergoes reduction to give the carbine species, which is N R air N R air N R air. So, that when treated with K potassium CH2PH in benzo 15 crown ether, crown 5 ether, then one gets this carbido complex C minus molybdenum N R air N R air N R air, and this being a minus, it has a counter anion is benzo 15 crown 5 potassium plus. So, this is an interesting example where a carbine moiety is efficiently converted to a carbido moiety, where there is this no substituents on the carbon, and it is bare carbon bound to metal. This is the ultimate organometallic ligand, and these are called carbido ligand, and they can be prepared for transition metal carbine complexes where R is only hydrogen. This is a nice example of how this reactivity has been achieved, and this is something which is unique to carbine complexes, and there is no such parallel that is known for the carbene complexes in terms of they being converted to carbido ligand. Now, with this we come to our end of the discussion on transition metal carbine complexes, and we are going to now move on to an important class of compounds which are transition metal carbonyl compounds. These are very important class of compounds in the sense that a large number of studies have been carried out with these ligands. These are one of the compounds which are long known, have been studied a lot over over probably a couple of centuries. So, the chemistry of these compounds are well developed and also extremely interesting in terms of their structure, bonding and synthetic details. So, we are going to move on to an interesting compounds, or these are called transition metal carbonyls, and these compounds contain transition metal CO bonds, and these can be monitored both by NMR as well as IR spectroscopies. These transition metal carbonyl compounds are also important intermediate in many homogeneous catalytic reactions, as well as these serve as useful tool in electronic and structural determination of organometallic species. So, carbonyl compounds have really played a crucial role in quantifying the ligand strength or the electronic nature, particularly of its electron donating and electron withdrawing ability of ligands, in quantifying these ligands in the field of organometallic chemistry. Transition metal carbonyl compounds have played a long role and have also been studied a lot. So, with that pretext, I am going to talk about various kinds of transition metal carbonyls that have been developed, and we are going to see that like how these carbonyl compounds have evolved around this class of other organometallic compounds that we have just discussed. Now, with this introduction, let me just say that transition metal carbonyl compounds usually many of them are known for to be the binary compounds, or a binary metal carbonyl, where there is these are homoleptic complexes where there is no other co-ligands present with transition metal carbonyl compounds. And these, among some of the examples of these neutral are that of iron pentacarbonyl or diiron nonacarbylene. Okay. Similarly, there are examples of manganese, CO10, or from chromium, CO6, or vanadium, CO6. Now, one must note that there is nothing, no binary carbonyl known for group 4, no binary metal carbonyls known for group 4 transition metals, for example, titanium, zirconium, and hafnium. Now, reason being that these group 4 transition metals are electron deficient. These are electron deficient and cannot stabilize CO ligand. Now, this is an important observation from the perspective of the fact that the metal carbonyl bond has two kinds of interaction. For example, metal to carbonyl sigma donation, as well as metal to carbonyl pi back donation. Now, as group 4 transition metals, if the metal is electron deficient, if metal is electron deficient, then metal C pi CO back donation do not occur. As a result, the metal carbonyl bond is not stabilized. Okay. So, that is why these group 4 transition metals like chromium, zirconium, hafnium, which are extremely electron deficient, they cannot participate in metal to carbonyl pi back donation. As a result, their carbonyl complexes as binary neutral metal carbonyls are not known. On the other hand, the electron among electron rich materials, this is quite common, and not only it is common for the first row transition metal, but also the same can be seen for second row and third row with the corresponding the chromium molybdenum counterpart MoCO6, as well as tungsten CO6, or manganese one like technetium Tc2CO10 or ReTCO10 being known. Similarly, for ruthenium RuCO5 or Ru3CO12 is known, and similarly for osmium OS CO5 or OS3CO12 are all known. Now, not only it stops at carbon, it can go over to cobalt with cobalt which can move over to, let us say, cobalt, CO2, CO8 being known, and all the way one can go to rhodium, RH, 4 CO 12, or iridium, IR 4 CO 12 is also known, and finally to nickel tetracarbonyl is also known. So, what is seen though over here, that the center of the periodic table from group 6 to group 9, almost for all the transition metals in first row, second row, third row, a lot of binary metal carbonyl complexes are known, and that is because these from group 6 to group 9, that these are electron rich metal centers, and that the metal is has enough electron density to participate in metal to ligand pi back donation. As a result, the binary compounds are stable. So, with this let me conclude what have been discussed in today's lecture. We started off by looking at transition metal carbine complexes. We looked at their reactivity from the perspective of how they were synthesized, and what we had observed, that the much of the reactivity of transition metal carbine complexes lead to the formation of transition metal carbene complexes, and this is similar to that we had seen earlier, where transition metal carbene complexes under suitable manipulation gave the transition metal carbine complexes. We have looked at the reactivity of transition metal carbine complexes in this regard with respect to the addition of the protons, where it can add to the metal or it can add to the carbon as the situations would demand based on the ligand and the metal environment. We have also seen an excellent example where transition metal carbine complex, where carbon had a hydrogen substituted on it, could be converted to the ultimate organometallic ligand, which is transition metal carbido complex. This was an excellent example, and the final complex was also structurally characterized using, and these complexes first was indeed stabilized using bulky ligand, and then they were succeeded in structurally characterizing it. We have with that we have looked into some other reactivity of transition metal carbine complexes, and then moved on to another pi acidic ligand, which are metal carbonyls. Metal carbonyls are long known compounds in the area of organometallic chemistry, unlike the transition metal carbene or carbine complexes which we had discussed, which were only known since the last 20 or 30 years, whereas metal carbonyls in organometallic chemistry had existence over centuries, or maybe to over 2 centuries. So, these compounds have been studied a lot, and they have been used successfully in quantifying the electronic nature of many other organometallic ligands, and that was one of the utility of transition metal carbonyl complexes which is emerged out. Also, transition metal carbonyl complexes are important intermediates for many catalytic reactions, particularly hydroformylation done with cobalt carbonyl or rhodium carbonyl compounds. And then we moved on to the binary transition metal carbonyl compounds, and what we saw that these binary transition metal carbon compounds are mainly dominant in the middle of the periodic table from group 6 to group 9, where these complexes exist for all the metals from first row to second row to third row, and that is because that these carbonyls are stabilized by electron rich metal centers, which can not only can accept electron by sigma donation, but also can back donate electron from the metal to the ligand, and this back donation is very critical in stabilizing transition metal carbonyl complexes. This is evident from the fact that for the electron deficient group 4 metals like titanium, zirconium, hafnium, no binary carbonyl complexes are known and are yet to be stabilized. So, with that I would like to conclude today's lecture, and we are going to be discussing bit more details this metal carbonyl chemistry, this exciting piece of chemistry, and we would see how these compounds have been developed in the area of organometallic chemistry, right from their synthesis to properties and their application studies, and that would be the subject of topic of next lecture. So, I thank you for being with me in this lecture and look forward to being with you, where we are going to be discussing the metal carbonyl chemistry in detail in the next lecture. Till then, goodbye.